My name is Mohammed Layiq Sediqi, and in this part of our Holophase journey, I want to do something very simple and very ambitious at the same time. I want to tell you a story made out of equations, but in a way where you don't need any maths background at all. You don't see the equations on the screen, you're just hearing them as words. So my job here is to translate each core formula of the Holophase model into human language, with examples you can picture and tests you can feel. Because these few little equations are not decoration, they are the skeleton of the whole model. And remember, at the heart of Holophase is not poetry, but falsifiability. Everything I tell you must be open to being wrong. So as we go through these ideas, we will keep asking, if this is the wrong way to understand reality, how would the world have to behave for us to see that? Before we begin, one important note. If you are a listener who wants to go deeper into the technical details, the formal Holophase papers with full maths, full definitions, and real lab protocols are being uploaded as preprints on Zenodoba. Some of them are already there, others I'm still preparing and uploading, so if you go there and don't see everything yet, please be patient with me. This project is big, but there are already serious detailed papers you can read and check for yourself. Here, in this episode, we'll stay at an introductory level, but I will not lie to you. I will tell you what the equations actually say in ordinary language. Let's start with the simplest idea of all. Merdi. 1. The world as one hidden rhythm. The Holophase model begins with a bold picture. Underneath everything you see, matter, light, fields, forces, even your own thoughts, there is a single continuous rhythm running through the universe. We give that rhythm a name. 509, you can think of it as phi. Now imagine that at every point in space, this rhythm has an oka angle, like the position of a hand on a clock face. If the hand is pointing straight up, you might call that 0 degrees. If it is turned halfway around, that's 180 degrees. If it is turned all the way around, that's 360 degrees, and then it starts again. So phi is like an invisible hand on a circular dial, at every point in the universe, always turning, always shifting relative to other points. You never see phi directly, you only see differences. How much phi here differs from phi there? How much phi now differs from phi a moment later? Those differences show up as time, how fast the hand turns, space, how the angle changes as you move, motion, how patterns of the angle slide around. The first equation that captures this idea is conceptually very simple. Phase now equals how fast the rhythm turns times time passed plus where it started. In more mathy words, that's phi of t equals omega times t plus phi naught. But you don't need to remember the symbols, just keep the picture. The rhythm has a speed of turning. The longer you wait, the more the hand turns. Where it is now depends on how fast it turns and how long it's been turning. This is the heartbeat of Holophase. Things are not made of little billiard balls, they are made of patterns in this turning rhythm. Now let's see how this simple idea gives us time, distance, and speed. That's 2. Time, clocks as rhythm counters. Let's begin with time, because that's the one you feel inside your own body. 2.1. What every clock really does, look at any clock you know. A wall clock, a wristwatch, your phone, an atomic clock in a national lab. Inside every serious clock, something is repeating. In a pendulum clock, a weight swings left, right. So in a quartz watch, a tiny crystal vibrates back and forth at a very stable rate. In an atomic clock, atoms flip between internal states in a steady rhythm. Each one is like a tiny drummer beating time. The clock simply counts the beats. Here are 2 small equations you already know without realizing. 1. Time to finish one cycle equals 1 divided by how many cycles happen per second. If something swings twice per second, one full swing takes half a second. If something swings 1,000 times per second, one swing takes 1,000th of a second. In maths, people write this as t equals 1 over f mum, where t is the time per cycle and f is the frequency, how many cycles per second. But in human language, the faster it beats, the shorter each beat is. 2. Phase from time, how far the rhythm has turned equals speed of turning times time. If the hand turns one full circle each second, after half a second, it has turned half a circle. In math language, we write phase equals frequency times time plus starting phase. In human language, how far around the dial we are depends on how fast we're turning and how long we've been doing it. So every clock is really two things at once: a physical rhythm, a thing that repeats, a counter that says we are now this many beats away from some starting point. 2.2 time as how much phi has turned. Holophase takes this very literally and says time is how much the underlying phi rhythm has turned. When 1 second passes, phi has turned by a certain amount. When an hour passes, it has turned much more. When no time passes, phi has not turned at all. You can think of phi's speed of turning as a master frequency. In ordinary physics, we already talk like this: the frequency of light, the frequency of a clock, the frequency of a wave. Holophase says this is not just a convenient language. This is what time is, the rate of change of phase. 2.3 A falsification test for time. Now, remember, Holophase is not allowed to hide behind pretty metaphors. We must always ask, what would the world have to look like for this to be false? So here is a very simple test. Could someone build a fundamental clock that does not rely on any repeating rhythm at all? That would be no swinging, no vibrating, no atomic transitions, no rotating Earth, no pulses or cycles anywhere. Just a device that somehow reads time itself with unlimited precision without ever counting anything that repeats. If such a device existed, genuinely, not just in marketing language, then the Holophase claim time is how much phi has turned would be in trouble. Because then you would have a way to touch pure time directly without going through rhythms. But in real life, as we make clocks more precise, we always end up doing the same thing. Find a more stable rhythm. Count its cycles more carefully. That's exactly what we do when we move from pendulums to quartz to atomic clocks. So our first little equation, time per cycle equals 1 divided by frequency, is not just a math fact. It's a clue that time is the bookkeeping we do on top of a deeper rhythm. Botchitike 3. Space, distance as how much the rhythm twists between here and there. Now let's turn to Oitite space. What does it mean to say these 2 points are 3 meters apart? We tend to picture a kind of invisible grid, a cosmic graph paper. But how do we actually measure that grid? 3.1 from rods in a vault to light in a vacuum. For a long time, the answer was we keep a metal rod in a controlled room and declare the distance between these two scratches on this rod is 1 meter. That's better than nothing, but it has problems. The rod expands and shrinks with temperature. It can bend or wear out. It lives in one single place on Earth. Modern physics does something smarter. We define the meter using light and time. So, the idea is simple. Light in a vacuum travels at a fixed speed, call it size. If we know how long it takes light to go from A to B, we can say distance equals speed times time taken. In words, how far light travels in a certain number of phase cycles is our unit of length. So the first distance equation is really just distance equals speed times travel time. If light takes 1/1000th of a second to go from here to a mirror and back, we can compute how far away the mirror is. But remember, time itself, we're measuring by counting cycles of some rhythm, like an atomic clock. So in the end, distance becomes how many light waves fit between here and there. 3.2. The twist of phase, how waves encode distance. Now we add a slightly deeper idea, still in simple language. A wave, like light or sound, has a wavelength, the distance between one crest and the next crest. It also has a phase twist, how fast the internal rhythm rotates as you move through space. Imagine painting a stripe pattern along a road. Bright stripe, dark stripe, bright stripe, dark stripe. If you walk along the road, the number of stripes you pass tells you how far you've gone. The math way of saying this is phase difference equals how tightly the stripes are packed times distance. Or phase difference equals spatial twist rate times distance. That spatial twist rate is just a fancy way of saying how many waves fit into each meter. So if the stripes are very tight, many per meter, a small distance causes a big phase change. If the stripes are wide apart, few per meter, you need to move further to get the same phase change. This is exactly how the interference measurements can work in optics. You send light along two paths. You recombine them and look at the bright and dark fringes. 3.3. The holophase reading of space. Holophase looks at this and says, space, as we measure it, is a way of describing how phi changes from place to place. If phi changes very quickly as you move a tiny bit, we say things like short wavelengths, or strong gradients, or tight patterns. If phi barely changes over large distances, we say long wavelengths, gentle gradients. So one of the core holophase equations for space, in words, is phase difference between two locations equals how strongly phi twists in space times the distance between them. 3.4a falsification test for space. Now we apply the same scientific honesty. What would show that this is not the right way to think about space? Here is the test. Can someone define and measure distance with extreme precision without using any waves, any phase differences, any timing of signals at all? In other words, no lasers, no radar, no sonar, no interferometry, no GPS-like timing, just some method that directly reads pure distance from the universe, independent of any oscillation. You might say, we can just line up rigid rods, but then we must ask, how do we guarantee those rods are really the same length? How do labs across the world agree their rods match? In practice, modern metrology always falls back on light and timing to calibrate nor lengths. So as of today, every really sharp distance measurement sends something that oscillates, makes a wave or pulse, then reads off phase differences, EDs, or travel times. Holophase says that's not a coincidence. That's how space is woven into our physical reality as phase structure. If one day we find a totally different, deeper way of measuring length that cannot be turned into phase language and that works better than all wave-based methods, then the holophase space from phase story must be updated or abandoned. Until then, the way our best rulers behave is evidence that space is how much phi changes across locations. 4. Motion, speed as how fast the pattern in phi moves. Now let's turn to your motion. This is the one we feel most obviously. We say, the car is moving at 60 miles per hour. The planet orbits the sun. The electron is traveling through the detector. But what are we measuring goids when we say something is moving? 4.1 Patterns moving versus stuff moving. Return to our favorite image, the stadium of lights. Each person has a little light they can flash on and off. Suppose they flash with a common rhythm, but not all in sync. Instead, the bright spots form a wave nights that moves around the stadium. What's moving? The people are sitting still. The stadium is not rotating. What moves is the pattern of brightness. Motion here is not bits of matter sliding along. It is phase features. Certain configurations of the hidden rhythm, drifting through the crowd. The surface of the ocean behaves similarly. Water molecules mostly bob up and down. The wave crest travels forward. That crest is just where the phase of the water's motion lines up in a certain way. Sound waves in air are the same story. Air molecules jiggle. Zones of high and low pressure travel. Those zones are patterns in the phase of molecular motion. Shutters 4.2. Everyday speed measurements are pattern trackers. Now look at how we measure speed in real life. The speedometer in an old car literally measures how fast the wheels are turning. Wheel turning is a rotation, a phase cycle. The device measures how many turns per second. Knowing how big the wheel is, it converts turns per second into meters per second. A radar gun sends radio waves toward a car and catches the reflection. If the car is moving toward the radar, the reflected wave's frequency is slightly higher. If it's moving away, slightly lower. This is the Doppler effect, a direct consequence of phase piling up faster or slower. From this frequency change, the device infers speed. Your doctor phone's GPS measures how your position changes over time. It listens to phase-coded signals from satellites. From tiny timing differences, it reconstructs your path. Then, it divides how far you've moved by how long it took. speed equals distance divided by time. In every case that really matters, speed is not how fast a mysterious stuff called motion is flowing. It is how fast some trackable feature of the world moves between places. In wave language, that feature is often defined by a specific phase condition, like where the phase is zero or where the amplitude is maximum. So one of the key Holophase equations for motion, in words, is speed equals how much distance a phase feature covers divided by how much time it takes. That's just our familiar. Speed equals distance divided by time. But for waves, we can say something even more revealing. Speed of the pattern equals how fast phase changes in time divided by how fast phase changes in space. Think of it this way. If the rhythm is changing very fast in time, but only slowly across space, the pattern has to move quickly to keep the same phase. If the rhythm changes slowly in time, but strongly across space, the pattern can move more slowly. Again, you don't need symbols. Just remember, speed is the ratio between a time change and a space change in phi's pattern. The Gusteda 4.3, a falsification test for motion. Now we ask our honesty question again. What would show that this is not how motion really works? Here is the test. Can someone measure speed in a clean way that does not track any moving feature, any phase change, any timing difference, nothing at all that travels? That would mean no wheels turning, no pulses propagating, no phase shifts, no bright blob tracking on a screen, no timing of signals, just a device that reads off your speed directly from some static configuration with no movement. If such a thing existed and outperformed all our current phase-based methods, holophase would have a serious problem, because then motion could not be pattern propagation in phi. But everything we trust right now, in traffic enforcement, in science, in navigation, is built from tracking patterns. That's why in holophase, the motion equation speed equals distance change divided by time change is really speed equals phase pattern shift in space divided by phase advance in time. Basit 5, all three dimensions working together, GPS as a living example. So far we have treated time, space, and motion separately. But in reality, our best physical systems use all three at once. The clearest everyday example is something you might have used today. The GPS system that tells you where you are. 5.1. What GPS actually does. Think about what happens when your phone says, you are here, moving at this speed in this direction. It has never seen you. It has not sniffed your environment. All it has is signals from satellites. Those satellites each carry very precise atomic clocks. They continuously broadcast messages like, right now, my clock reads this number. Those numbers are really just phase counts. I have done this many cycles since my starting point. Your phone receives those signals at slightly different times from different satellites. For each satellite, it can ask, what did the satellite's phase count say when it sent this signal? What does my own phase count say when I receive it? From the differences, it can compute how far away each satellite is using distance equals speed times signal travel time, where in space you must be given those distances, and how your position is changing in time, your velocity. So GPS is a system where time comes from phase counts in atomic clocks, space comes from how long signals, waves in pi take to travel, motion comes from how quickly your phase relative position changes over time. All three are read from one web of rhythms. 5.2. The altogether consistency test. This gives us our fourth falsifiability check. Can we always describe time, distance, and speed measurements of a system as consistent readouts of one underlying phase structure? In GPS, the answer is yes, that's literally how it works. But imagine some future experiment where our best time measurements, our best distance measurements, our best speed measurements flatly refuse to fit together into any phase-based description. We haven't worked it out yet, but it is impossible in principle. If such a domain exists, then the holophase claim, time, space, motion are three faces of one rhythm would be in serious trouble. part of the Holophase research program in the technical papers on Zenodo and those still being uploaded is to confront this, to work out where the phi description succeeds, to identify precise conditions under which it might fail, and to propose experiments that could expose those failures. Because if Holophase cannot survive this altogether test in the real world, then it does not deserve to be a fundamental model. Darad 6. Why these little equations matter so much. At this point, you might reasonably ask, okay, I understand that clocks, rulers, and speedometers are all rhythm tools. But why are these little equations such a big deal? Why do you say they are the heart of the model? The answer is that each of these tiny formulas is like a line of DNA in the holophase organism. Let's list them again in human language. 1. Phase from time. Phase now equals how fast the rhythm turns times time passed plus starting phase. 2. Time per cycle versus cycles per second. Time per beat equals 1 divided by beats per second. 3. Distance from signal travel time. Distance equals speed of signal times how long it took to arrive. 4. Phase difference versus distance. Phase difference between here and there equals how tightly the wave's pattern is packed times distance. 5. Ordinary speed. Speed equals how much distance changed divided by how much time changed. 6. Wave pattern speed. Speed of the wave's pattern equals how fast phase changes in time divided by how fast it changes in space. Individually, each one of these looks like a simple physics fact. Together, they form a consistent story. Time is a way of counting phase turns. Space is a way of comparing phase across locations. Motion is a way of tracking phase patterns as they slide. The holophase model says, take this seriously. Don't just treat phase as a technical detail. Treat phase ifhai as the actual substrate of reality. Then rebuild energy, space-time, forces, quantum behavior, even information and life as patterns in phi and its derivatives. In the formal papers, these little equations grow into a full mathematical framework with derivatives, rates of change, with fields, phi as a function over space-time, with conservation laws, with experimental gates and error budgets. What I'm doing here with you is keeping that framework anchored, not in abstraction, but in the devices you hold in your hands and in tests that could break the model. Topecast 7. Falsifiability at the center. Let me pause and underline this because it is easy to miss. The greatest strength of Holophase is not that it sounds deep. Its strength is that it can be killed by evidence. Every core claim we have made comes with a key kill switch. If someone builds a non-rhythmic fundamental clock that bypasses all cycles, the time from phase picture must be revised. If someone invents a distance standard that beats all wave-based methods and cannot be written in phase language, the space from phase claim weakens. If someone measures speed in a completely non-dynamical way, no patterns, no phase, no timing, motion as phase propagation is challenged. If we find a domain where time, space, and motion measurements cannot be fitted into any underlying phi structure, the dimensional unity claim cracks. In the more technical side of the project, which you can explore in the Zenodo preprints, these ideas are turned into explicit gates, conditions you can check, algorithms you can run, inequalities you can test in data. Here, in this episode, we keep them as simple questions you can carry in your mind. If you remember nothing else, remember this habit. Whenever you hear a big claim about reality, mine or anyone else's, ask, what kind of measurement would show this to be false? If there is no answer, you are not dealing with physics. You are dealing with a story that cannot lose. Holophase wants to be the opposite, a story that can be proven wrong. That's the only way it earns the right to possibly be right. Sector 8th. Where we go from here, let's gather where we have reached in this episode. We started with a simple picture. The universe is threaded by a single continuous rhythm. Phi-aj, Ida. At every point, phi has an angle on a dial. What we experience as time, space, and motion are different ways of reading patterns in this angle. We then walk through the core equations of that picture in plain language. How phase depends on time, how time per beat relates to beats per second, how distance can be read from signal travel time, how phase differences encode geometry, how speed is distance change over time, how wave pattern speed emerges from phase changes in time and space. We tied each of these to real devices, clocks that count cycles, rangefinders and interferometers that read phase, speedometers and radars that track moving features, GPS systems that combine all three dimensions from one web of signals, and we placed falsifiability at the center by asking what kinds of devices or experiments could break the holophase picture. Along the way, I reminded you that the full mathematical story, with all the symbols, derivations, and protocols, lives in my holophase papers, which I am gradually uploading to a Zenodo. Some are already there, others are coming. If you're a scientifically trained listener, you can go there, look up the work, and check whether what I'm saying here matches the equations and methods in those documents. What we will do next in future episodes is take this operational foundation and move into even deeper territory. How does changing the rate of the rhythm alter our experience of time? How does reshaping the spatial pattern of phi bend what we call space? How do different phase structures give rise to what we currently call forces, fields, no, and even mass? And eventually, how does this single phase model touch information, life, consciousness, and meaning? But we will only allow ourselves to move upward if we keep our feet on the ground, on clocks, on rulers, on speedometers, on experiments that anyone can in principle repeat, because only then can we honestly say, this is not just my private vision of the universe. This is a model that reality itself has had a chance to argue with. Thank you for listening and for being willing to walk through equations without seeing them, only hearing them as stories. In a way, that is already very holophase. You did not see the symbols directly. You heard patterns of sound and built meaning from them. Just like we never see phi directly, but we see its patterns and build a world. In the next episode, we'll start exploring how this hidden rhythm does not just sit there quietly, but bends time, reshapes space, and drives motions in ways we can test, question, and, if we are lucky, understand.